Hey everyone, welcome to this explainer. If you've ever wanted to pull back the curtain on data science and see exactly how a machine learning model is constructed from the ground up, you are in the perfect place. Today, we're treating this whole process like a straightforward, step-by-step recipe. By the time we wrap up, you'll know exactly how to mix raw data with Python and Google Colab to cook up a working predictive algorithm. We're keeping things super practical and totally focused on the actual steps you need to get it done. We're going to tackle this in 5 simple stages: setup and loading data, slicing and splitting, building the models, evaluating them, and finally visualizing the results. Let's get right into it. Step 1. Setup and loading data. So we're firing up Google Colab, which is a fantastic free coding environment, to gather our main ingredient, the Delaney dataset. We're looking at molecular solubility data here, specifically a metric called log S. Now, this is absolutely crucial for biologists and chemists because it literally helps them predict if a molecule is going to dissolve well in water and actually make a viable drug candidate. So the stakes for these predictions are very real. Our data comes packed in a standard CSV file. To bring this raw text into our Python environment, we're importing a powerhouse library called pandas, usually under the alias PD, and loading that CSV straight into a data frame. You can think of a data frame, affectionately known as DF, like a supercharged spreadsheet running right inside your code. It takes all those messy, jumbled, comma-separated values and perfectly organizes the whole shebang into nice, readable rows and columns. All right, moving on to step 2, slicing and splitting data. We can't just dump our entire data frame into a model and hope for the best. We've got to purposefully slice it up. Think back to that classic y equals the function of x equation from algebra. We want to predict our y output based on our x inputs. In our Delaney dataset, we've got 4 distinct columns acting as our x variables. These are independent molecular features, stuff like molecular weight. We need to separate those from our single dependent target variable, the y variable, which is that all-important log S metric. By simply dropping the y column from the x set, we cleanly isolate our inputs from our output. Once we've got them separated, we lean on the scikit-learn library to do some vital data splitting. We take our full data set of 1,144 rows and randomly divide them into 2 buckets. 80% becomes our training set, and the remaining 20% is our testing set. We're also setting a random state, say the number 100, just to make sure the split is completely reproducible every time we run the code. That 80% is what our model actively studies to find patterns. The 20% is locked away like a blind final exam to see how well the model actually handles completely unseen data. Which brings us to step 3, building the models. Time to actually cook up these machine learning algorithms. We're starting with an absolute classic, linear regression. We just import this directly from scikit-learn's linear model library, and then we hit it with the .fit command. We feed it our 80% training data, both the x inputs and y targets, and let it establish those fundamental mathematical relationships between our molecular features and the resulting solubility. But why stop at just one model? Since our y variable is a continuous quantitative number, we are firmly in regression territory. So let's train a second, slightly beefier algorithm called a random forest regressor, just to see if it outperforms our basic linear baseline. We import it, set a couple of quick parameters, like a max depth of 2 and our trusty random state of 100, and fit it right to the training data. Boom. 2 models, trained and ready to go. Step 4, evaluating model performance. Okay, the models are built, but now we need that taste test. How well do they actually predict that hidden 20% of data? We generate predictions and then grade them using 2 metrics from scikit-learn. First up is mean squared error, or MSE, which basically checks how dispersed our errors are. A lower MSE is exactly what we want. It means our predictions are tightly clustered around the true values. Then we have the R-squared score, which evaluates the overall correlation. To make sense of all these numbers across both our training and testing sets, we can use the pandas concat function, short for concatenate, to smash our individual results into one gorgeous unified data frame. It gives us a really clean, side-by-side tabular comparison of linear regression versus random forest. And honestly, building a comparison table like this is a massive game changer. It sets you up perfectly to just drop in even more complex models down the line and instantly see how they stack up. Finally, step 5, visualizing the results. Tables are great for precise evaluation, but nothing beats a solid visual. We're generating a scatter plot using matplotlib to map our predictions against reality. The x-axis is the true experimental log S, and the y-axis is our predicted log S. We're making it a nice 5x5 square with green data points. But the real trick here is setting the alpha parameter to 0.3. That gives our dots a bit of transparency, meaning wherever the predictions heavily overlap, the green naturally gets much darker. It creates an instant heat map of our highest density prediction areas.
To really make this plot pop, we're dropping in a stark red trend line using NumPy's polyfit function. Think about it. If a model was 100% flawlessly accurate, the predicted values would exactly match the experimental ones, creating a perfect diagonal line. By slapping this bold red line right through the center of our green scatterplot, we get immediate visual confirmation. The closer those green dots are hugging that red line, the better our model nailed the prediction.
So we've taken raw, comma-separated text and transformed it into a fully visualized machine learning prediction. I want to leave you with a fantastic quote from the creator of this tutorial. The best way to learn data science is to do data science. You've got the exact recipe now. So here's the real question. If this relatively simple setup can accurately predict molecular solubility in a matter of minutes, what kind of massive real-world problems could you solve just by swapping out the dataset? Open up Colab, grab some data, and find out for yourself. Thanks for tuning into this explainer and have an awesome time building your own models.